Hello everyone. In this video, I will talk about the SPM, a real leveling method that tries to improve NAND flash chips' lifetime in solid-state drives. I am Asal Khanbadr and recently received my master's degree in computer architecture engineering from Khwarazmi University in Tehran. First, I start with an introduction, and then some related works are reviewed. Then I describe the SPM method's details and its main goal, and after that, simulation results are represented. Finally, I conclude the presentation, and last slides are references. Now let's see what components solid-state drives have. A microcontroller is the main component of an SSD. It runs flash translation layer firmware and it is responsible for transferring data between host and NAND flash chips. And it is typically using a DRAM as its working memory. Host interface is responsible for queuing requests and delivering the responses. Flash chip controller is another component of an SSD and it generates control signals. NAND flash chips in the same group are connected to flash chip controller through a same channel. As you can see in the right figure, a NAND flash chip contains multiple dies, and each die contains multiple planes, and each plane consists of several blocks, and each block consists of several pages. Each die has its own command and address registers, which enable it to serve requests individually. Now let's talk about flash translation layers, which do three main tasks. In address translation, FTL maps logical addresses of requests to physical page addresses, and garbage collection module increases the number of free blocks when the number of free blocks is below a certain threshold. It selects one or more victim blocks and after transferring their valid pages to other blocks, they will be erased. And finally, because the NAND flash memory has limited lifespan, via leveling would ensure all flash blocks are raised evenly. NAND flash memory has two main limitations. First, raise before write. Data should always be written to raise flash pages, and an raise operation must be performed on a block before it can serve write requests. So the out-of-place scheme is employed to write updated data, and the memory occupied by invalid data should be reclaimed later by invoking garbage collection. And the second limitation is the limited endurance of flash memory. Each flash block can endure only a limited number of write-erase cycles, and after the finite number of erase program cycles, the flash block is not reliable to serve write requests anymore. Now, let's review some related works. First, efficient victim block selection or EVBS. EVBS employs a data structure containing a group of arrays that help the garbage collector to select a region of blocks containing the most invalid pages. This method would improve the lifetime of flash memory. However, if the number of blocks in a region increases, the performance may be degraded. Second method is progressive via leveling or PWL that tries to raise flash evenly. In this method, during the via leveling, a block which is raised less than the average of blocks raised count and its data is accessed less than others is selected to be erased. This method improves flash memory endurance, while the way in which it estimates least frequently accessed data is not directly related to how recently the data was accessed. And third method is qubit via leveling or qubit WL. In this method, for each block, a qubit flag saves the block's erase count. If all bits of the raise flag of a block are set to ones, then a block whose all qubits are zeros is selected, and its valid data is transferred to the recently erased block. The accuracy of this method may be improved if the frequency of data access is taken into account. Erasure interval-based garbage collection or EIGC is the next method. In this method, uh, an erasure interval between two successive blocks erased is defined. The interval and non-interval parameters are used to estimate the cost of each block, when a victim block should be selected during garbage collection. The cost estimation of this method might be time-consuming under specific workloads. And finally, the earlier version of this paper, or the scoring-based method. This method utilizes two separate queues for each plane to hold scores of the erased and allocated blocks. Each queue may contain one or two sorted arrays of block scores. While this method improves flash memory endurance considerably, it needs a sheaf to keep arrays sorted, which degrades the performance. Okay, let's review the main goal of the SVM. The SVM method tries to improve the lifetime of flash memory by raising flash blocks as even as possible. Now it's time to talk about more details about the SVM. The SVM and its earlier version used three data structures: the global block table and two priority queues. However, in the SVM, priority queues are managed differently. An raised blocks priority queue holds raised blocks scores, and it is a single min-heap. Min-heap is a complete binary tree in which each node's key is less than or equal to its child node's keys. An allocated blocks priority queue holds allocated block scores, and it is typically consists of two separate min-heaps. And finally, the global block table. The global block table stores all blocks residing queues, which is allocated or raised, and the index of each block's metadata in the corresponding priority queue. It's time to talk about events that affect block score. The block scores are zeros at the initial stage, and three events change block scores. Two events increase a block score. When a block is raised, its score is increased by 2 points, which result in better endurance based on simulation results. In the earlier version of the SVM, only 1 point is added. And second event is writing a flash page, which will increase a corresponding block score by 1 point. And one event decreases a block score. When a page is invalidated, its corresponding block score is decreased by 1 point. Three factors affect the victim block selection in the SVM. First, the number of valid pages in a block. Copying valid pages from a victim block to another block can have an adverse impact on garbage collection performance. So, more valid pages in a block should increase its score. And second factor is the erase count of a block. The age of a block indicates raise count of a block, and older blocks have been more raised in comparison with other blocks. In victim block selection, blocks that have less raise count should be selected. Higher raise count should increases the block's score. And finally, temporal locality, which indicates that the same data is more likely to be accessed repeatedly during a short period of time. So, the recently written data are more likely to be invalidated. So, the blocks which recently served write requests should not be selected as a victim block. The SPM uses two different parts for insertion in and removal from allocated blocks priority queues to prevent selection of blocks which contain the recently written data. Uh, in this slide, we can see an raised blocks priority queue, which is a single min-heap. In this min-heap, scores are twice the value of raise count of a block, and each node's score is less than or equal to its child node's scores, and free element indicates don't care elements. This slide shows an allocated blocks priority queue, which typically contains two separate min-heaps. Newly allocated blocks metadata is inserted into an insertion min-heap, and victim blocks are selected from removal min-heap. When the last element in removal min-heap is removed, removal min-heap and insertion min-heap will be swapped if the queue is not empty. A point should be noted here. At the initial stage or when allocated blocks priority queue is empty, or when all blocks are raised, the insertion and removal pointers are pointing to the same index. After the first element was removed, the insertion index is updated to point to the other side of the array. When a free block or a victim block is required, an element should be removed from an arrays or allocated blocks priority queue. Consider this is a removal min-heap in allocated blocks priority queue. After the victim blocks metadata is saved, the last element in the last level of min-heap is copied to the root. After that, it will be deleted from the tree, and the node's score will be compared to its child node's scores. If its score is greater than one of its child node's scores, they should be swapped. The algorithm continues to swap until the node is a leaf node or its value is less than or equal to its child node's scores. When an element is removed from one queue, it should be inserted into another queue. The new element should be inserted into first free spot in the last level of min-heap, and it should be repeatedly swaps with its parent until it is a root node or its value is greater than or equal to its parent node's score. The nodes in allocated blocks priority queue will be updated. When a score is increased, uh, it should be compared to its child node scores. If it is greater than one of its child nodes, they should be swapped. The node continues to swap until it is a leaf node or its value is less than or equal to its child node scores. On the other hand, if an element score is decreased, it should be swapped with its parent nodes until it is a root node or its value is greater than or equal to its parent node's score. The SPM and related works are implemented using SLSystem, which is an event-driven simulator. Uh, the source code of SLSystem was modified to better estimate the endurance and performance of non-flash memory. Three benchmarks are utilized. First, IOZone. IOZone is a write-intensive benchmark, and it consists of 99% write requests. It was run in an automatic mode. FIO is a synthetic benchmark, and it was customized to contain 70% random write requests and 30% random read requests. And the size of each request is about a flash page size. And Bunny++ is a read-intensive benchmark and consists of about 2% write requests. First parameter is standard deviation of erase count of locks. As you can see, the proposed method outperforms other methods. It improves endurance by 5.5% and 2.5% compared to its earlier version, and by 54.6% and 39.6% compared to third best method in IOZone and FIO benchmark. In FIO benchmark, while the FIO benchmark contains fewer and smaller write requests, which are served in blocks across all channels, the flash blocks are less erased and more evenly erased. So our method shows a better result in FIO benchmark compared to IOZone. Moreover, PWL is a method in which accuracy decreases more than other methods when the number of requests and their size increases. The SPM is earlier version and EVBS are showing stable results in IOZone and FIO benchmarks. While in Bunny++ no erase operation is done, all results are zeros. Next parameter is erase count of locks. In both write-intensive workloads, the SPM erase count is nearly equal to its earlier version. In IOZone benchmark, all methods are virtually at the same level, and EIGC needs the fewest number of erase operations. And the SPM method result is about 2% more than EIGC method. In FIO benchmark, EVBS needs fewest number of erase operations, and the SPM method result is about 7% more than EVBS. And COVID WL shows the most performance, and its value is about 43% more than EVBS method. Average write response time in terms of milliseconds is shown in this figure. In all three benchmarks, the SPM is the fifth best method. In both write-intensive workloads, the SPM result is about 1% more than its earlier version. Bunny++ contains about 2% write requests, which cannot be served until a considerable number of read requests are served. So, average write response time is higher for all methods in this benchmark. In Bunny++, EVBS outperforms other methods, while EIGC shows the worst performance, and its value is about 56% more than the SPM method. IOZone benchmark contains more write requests compared to other benchmarks, so the average is taken over more samples. COVID WL shows the worst performance in IOZone benchmark, and its value is about 36% more than PWL, which is the best method. EIGC, PWL, EVBS, the SPM and its earlier version are virtually at the same level. The SPM method result is about 1.3% more than PWL. In FIO benchmark, the SPM method result is about 14.3% more than EVBS, which is the best method, and EIGC shows the most performance, and its value is about 27.4% more than EVBS. Throughput in terms of megabyte per second is shown in this figure. In IOZone benchmark, all messages are roughly equal. The SVM message throughput is about 1% lower than its earlier version and about 6% lower than the best method, which is COBIT-WL. In Bunny++, EVBS outperforms other methods, while EIGC shows the worst performance. The SVM message throughput is about 7% lower than its earlier version. In Fire benchmark, the SVM message result is about 1% lower than its earlier version. And while the COBIT-WL shows the best result, EIGC shows the worst performance. In conclusion, the SVM can improve the lifetime of NAND flash memory by at least 2.5% compared to our last published paper and by at least 39.6% compared to the rest of the methods. And in addition, the SVM doesn't need any search routine for finding victim blocks. And finally, the time complexity of the main functions is big O of log n. The main functions are the removal, the updating, and insertion functions, and n is the number of blocks in a plane. Slides 24 and 25 are references. Thank you for watching this video. Do you have any questions?